research program. And last year he moved back to UNAM to join the ngVLA team there, as a sports scientist as well. And his task is to look at site selection and site characterization for the antennas in Mexico. We will hear more about that in the talk, I'm sure. His research interests include AGB stars and radio and submillimeter astronomy. And with that, please start the presentation.
Thank you. Thank you, everyone, for the opportunity to talk during this PITSA seminar. And I will essentially go over two topics during the talk. One is the project itself, the ngVLA project, in the design, a little bit of the outline for this project in the next decades, actually, and then a little bit of the science that you can, in principle, do with these kind of instruments. And okay, so this collaboration is well, it's a medium-sized group. All these are the collaborators mainly in Morelia, and on the right-hand side we have some people from Mexico City, also from the university, and then of course some people from NRAO that are all working on this project. Yeah, so let's get started. So the outline is essentially the description of the project, the timeline, some of the key science work, and the science goals that we want to achieve with this telescope, and then the project that the counterpart on the Mexican side for this large project. And then I want to emphasize that, similar as ALMA, for those ones that are familiarized with ALMA, the idea is that every astronomer and astrophysicist will benefit from this project, regardless if you are former radio astronomer or from optical or infrared or any other thing, right? Yeah. Okay, so a little bit of the history. So for those that are not familiarized a lot with this kind of telescopes or instruments, so this is the very long baseline array. And so this is a collection of 10 antennas with 25 meters of diameter. This is in the US, basically all the way from the southern part of the US to the northeast. The frequency coverage is here. Is not continuous, but this is the range that it covers. And then this is these telescopes, of course, you can use single dish observations if you want to, but the idea is that these ones are interferometer. So then the basic idea is that instead of having an antenna of this size, then you have an antenna of kind of like the continental size of the US with many holes in between, right? Because you only receive data from these tiny dishes compared to these gigantic distances. And this is the angular resolution you get. So you can see that in terms of angular resolution, these telescopes or this interferometry technique, it can surpass very easily optical telescopes or other observatories. Another counterpart for this, or another style of doing this observation, this is a very large array. This is sitting in New Mexico. And then the longest baselines here are the order of a couple 10 kilometers per second. Sorry, kilometers. Yes, these are baselines. And then these are the same design kind of antennas, 25 meters in diameter. The frequency coverage is a little bit different, but basically you can go all the way to 43 gigahertz or 50 gigahertz, which is already gives you an idea is getting close to submillimeter regime. Yeah, and the best angular resolution is this, and for this observatory. And then the idea is that this observatory didn't have these receivers at 50 gigahertz for a long time, or when it was built in the 70s. And then later there was a strong collaboration with Mexico through the CONACYT, which is the national agency for funding. And they put receivers basically at 40-something gigahertz to observe, for example, SIO masers and other molecular transitions. So they have been collaborating from the 80s pretty much. And then this brings me to the very large, to the new generation very large array. So the idea of this is of course an artistic impression of the future telescope. And then you can see that the dishes are not more like circles. These are not exactly parabolic in this design from here to here, because the focus is off center. So it's like kind of like a piece of the parabola in that sense. And then what is the new thing about this? Well, as you see in this case, we have 10 times larger sensitivity if you compare with the ALMA, which is this state-of-the-art submillimeter observatory in Chile, in Atacama, and then you have also 10 times higher angular resolution than that observatory. Of course, the frequency coverage is different, but if you compare at the same wavelengths, then you have this 10x sensitivity and higher resolution improvement over those observatories. And sure, how you achieve that, and where you have more than 218 meters antennas like this one, and then you have some other ones, 6-meter antennas in diameter that is kind of like a small array, where you can map larger angular scale in the sky, for example, similar to what ALMA does in a way. And then this is the idea is that it's going to be center the New Mexico, the current BLA site actually. And this is a project essentially from NRAO. And the idea is that it should be funded by NSF if it's successful or approved, yeah. And then the difference with ALMA or the BLA is that the antenna positions are fixed. So you cannot move antennas around. In the BLA, for example, that it has a design of a Y, like the Y letter. These are the two arms and the other arm here. You can actually spread them. And by doing that, you can improve the angular resolution. But you cannot do that with this because you have 240 dishes, so you cannot afford to do that. And the idea is that if you put them in a configuration good enough in terms of scientific productivity, you don't have to move them actually. So how does it look like, these 240 antennas? So we have a core of antennas that is here, all this cluster, each one of them is an antenna. So you can see they are really densely packed. And then you have these other kind of like spiral arms that are going outside. And then if you zoom out even more, then you have these other kind of like fingers going down into northern Mexico in this area. So this is the first spiral, and this is other kind of like another piece of spiral. And then on top of that, you also have other antennas here. This is Hawaii, and then you have here on the border with Canada and the Northeast US, and then something on the Caribbean. And the idea is that these antennas that are spread all over the continent are the future BLBA, the first picture I show you. And this one, this is spiral, and all this one is like basically the future ngVLA. So all this is called the same instrument, but you can tell that because the distribution of antennas is very different, then they are built for, I mean, the array is mapped in this way for different scientific purposes. We can go down to that a little bit later. And then if in terms of numbers, this is the frequency coverage, basically from 1 to 216 gigahertz. And then in the colors represent the ngVLA. This is kind of like the pink, dark pink area here. And then you have a SKA. For those ones that use the SKA, you have these bands, at least the phase one of the SKA, that is under 20 gigahertz, essentially in their lowest frequencies. And then you have ALMA, that is this other part, right? And then, of course, beyond 120 gigahertz, ALMA keeps going because ALMA goes to 600 or something gigahertz. Then, but this is just comparing the ngVLA coverage. And this one here takes into account the surface area of the antenna and also the sensitivity of the dishes and the system temperature and everything. So essentially, the highest points here really represent higher sensitivity. Or in other words, you can map things faster at the same sensitivity compared to other telescopes. And you can see the ngVLA is essentially, well, as mentioned before, 10 times better in that sense, right? So it doesn't cover all the spectral range like SKA or like ALMA, but essentially in this range that is covering, the idea is that you can bridge what the SKA can do in these frequencies and what ALMA can do on the right-hand side of this axis. And this is another comparison in terms of angular resolution. This is log scale here. And you can see this is the ngVLA coverage and frequency and also the angular resolution compared to the SKA, which is also a gigantic observatory, or will be. The current BLA here, you can see this one here. And then, of course, the SMA is here, is another submillimeter observatory. It's like a smaller scale. And then you can see here the footprint of ALMA. So this is only the region where the two telescopes will overlap. But you can see that even in this region, then the ngVLA can do much better. Yeah. Okay, so there is all these observatories are defined by many numbers. For example, the frequency coverage, the field of view, basically what the telescope can see at any time during the observations, and what is the frequency coverage you get, the angular resolution, and stuff like that, right? So all these ones are numbers in terms of millijansky per beam or per PSF, let's say it. But then anyway, these ones are available in the website for you to look at. So the collaboration that is building this, we will try to build this, and it's led by NRAO. This is a project from NRAO and NSF essentially. And the international partners are so far a few institutions in Japan, one in Canada, and then now the university in Mexico. So this is basically the directorship or the leadership of the project, led by the director of NRAO. And then in Mexico, we essentially have institutes inside UNAM as part of this collaboration. So a little bit of the outline or what we expect here, we can discuss, but let me first tell you that in the 2020, there was this ranking of projects in order of importance: optical telescopes, infrared, and also radio telescopes. And basically, this called a decadal survey. So basically, the ngVLA end up in a high rank in all these projects, and this is a timeline in years when they are going to start building and when they are going to start the operations, right? That's the ngVLA here. So in principle, the ngVLA should be kind of like ready in 10 years from now or something like that. A little bit more in detail. This is the decadal survey 2020. The idea is that the prototype antenna, which is like this one, would be delivered to NRAO for testing sometime at the end of this year, but in reality it would be like mid next year, 2024. And then, but the idea is that by the end of the decade, or maybe early in the next decade, the observatory will have enough antennas to actually be able to surpass the current VLA in capabilities. And then you should be ready for full science operation by the end of the next decade. So like 15 years from now, something like that. So as you can see, it's not a project that is going to be ready anytime soon. All this takes many years, for example, from the ALMA experience. But if you think into this year, like 15 years from now, then essentially the current generations, but mostly the next generations, or the people that is entering the field at this moment are going to be using this more like in a routine basis, right? That is the implication. So this is just numbers about how much the project cost. And this is on the order of $2 billion or 2.2, whatever, but this is 2018, before pandemic, and many other things, and the cost for operations. So just to give you an idea, this is on the order of what ALMA cost for the construction, at least. Operations may be different. So it's this kind of things. So as you can see, it's way cheaper than James Webb or other things, but of course, it's still a lot of money, right? So that is what has to be sorted out. Okay, so a little bit of the operations concept is very similar to what ALMA offers or what other telescopes now are offering, in the sense that the idea who to use this instrument is PI-led proposals. That is the first thing. The best science is the one that gets done. That is the general idea. And similar as to ALMA, the thing that ngVLA will do is that it will just build pipelines. So they process all the data for you. So you get what they call science-ready data products, right? Which is the current ALMA model, in which you don't have to actually go through the data yourself to be able to build images or data cubes. Of course, if you want to improve on that or modify, you have to do it. And yeah, and the idea is that the same as ALMA, there will be a team of people evaluating this in a scientific point of view. So yeah, so this is a telescope for everyone, not just for radio astronomers. Yeah. Okay, so there are basically a few key science goals. So these are the ones that essentially the Science Advisory Council or Committee came up with. And then also there's some study groups, for example, for galaxies, for quasars, for interstellar medium, etc. It doesn't mean this is the only thing you can do, of course. These are what the observatory identify as kind of like the main ones, but inside these categories, so there are more categories for everybody. So I'm going to go a little bit over these ones. It's just some examples. And as you can see, this one is a little bit mentioning what the team in Mexico has been doing in this regard. So this is a protoplanetary disk, and you can see all these rings. This is observed with ALMA in continuum at 1.3 millimeters. And then this is a synthetic, this is the BLA. But then the idea is that the ngVLA will be able to do much better than this. And here, scientifically or physically, different wavelengths. This is 7 millimeter, this is 1.3 millimeters. This is tracing basically dust emission, but with larger particles compared to this one. But one of the problems in these ALMA observations, even though they are very bright and very beautiful in a way, is that they are optically thick. So you can actually derive the physical parameters without much confidence. And at these wavelengths, the emission from the dust is more transparent. So in principle, you can see all of it. And then this is just a plot in these kind of systems in radius. And this one is dust temperature, the density, and then the size of the particles, right? So in principle, with different wavelengths, mark or different molecular lines, these ones, all these colors, you should be able to probe at different distances from the center part, the components of this disk, right? And this takes long observations with ALMA. So the idea is that ngVLA should do it much faster because of the capabilities. Some other case, for example, for those that work in massive star formation, and they have these H2 regions around it, basically ionized gas. And then some of the things that people is trying to do is to see how massive stars form. The idea now is that they start like a low mass jets. Basically, we have jets in many low mass stars, but they keep accreting material. And at some point, they have radio recombination lines, molecular. And then this one is density, and basically. And then you have the H2 region here. So some people is interested in the evolutionary scenario for massive stars, from jets all the way to what we know as an H2 region that is all kind of like round symmetry. Yeah. Some of the things that people is going to be able to do that, well, people already do this, but you can do this. All right, right. Oh, okay. I think you can still see it. So this is something astrometric studies. So essentially, you have this low mass star, and then you have a substellar mass object orbiting around, and then you see this kind of trajectory after you remove the parallaxes. So you see this just wobbling of the main star caused by this other companion. So these are the trajectories. Once you remove the component from this one, you remove the parallaxes, you enter with the astrometric signature, they call, and then later when you account for the substellar companion, then you basically enter with noise. So this is a way to infer companions in low mass stars, for example, that otherwise you cannot do. Yeah. So this is you are inferring the companion, right? You are not directly observing the companion, right? Yeah. See. Okay, I guess because of the video, I think no, it's okay. Okay, this is just another example, and from the similar type of exercises that people do. So this one is already possible to do with a long baseline, which is basically like the BLBA. Something happened with the video, but essentially in this system, you have the main star here, you have a component here, and then you can have basically a planet inside a system, right? Sorry about the video. But the idea of this is that if you look for these astrometric signatures, then you can infer the components of a system, right? Well, it's finally playing. So yeah, you have basically the main star after you account for the frame of the star, and then you have this companion. And then here, well, inside you have the planet circling the main star, right? But with a substellar companion outside. And this is a view from the planet itself, where you see the main star and then you see the companion orbiting, right? And so anyway, this is already possible to be done. The problem is that the current sensitivity doesn't allow you to do this in a systematic way. And also you cannot see very far in distance because you don't have the precision in the astrometry. Yeah. So some other people are interested in prebiotic molecules. So this plot basically represents a prediction of the ngVLA in terms of sensitivity in kilometers per second. So this is frequency where these molecules appear. And then just to give you an idea, if you do this with a current single dish antenna like the GBT, that is basically a 40-meter diameter telescope, you end up much higher in sensitivity. So you will, all these lines will be buried in the noise of the telescope. The blue line represents what the ngVLA prediction would be, and the different component in molecules, right? You can see, of course, there are things below this one, but it's to give you an idea how much better the ngVLA can do. Yeah, other people are interested in massive or submillimeter galaxies or dust emission from high redshift galaxies. This is, for example, what the 20 hours with the VLA can do. And the idea is that you do with this the ngVLA, you should be able to see, well, you should be able to do the same, but in a much shorter time. And if you do a higher redshift galaxies, then in principle, the resolution recovers this, right? So this is a synthetic model folded with the current VLA and the next generation VLA, right? So these kind of exercises people tend to do very often for new telescopes because you need to predict what the telescope will be able to give you, right? And some other people are working in pulsars or black holes in the galactic center, for example, or in some other galaxies. And then I'm not going to go into detail in this, but the idea is that you should be able to map and detect many more pulsars in the galactic center or the bulge of the galaxy for testing new theories of gravity or something. Yeah, so you also can do that. Because you also can do polarization, then you also can observe jets or other objects that give you polarized emission. This is the total intensity in continuum for the jet in M87, for example. This is the fractional polarization of the synchrotron emission, and this is the rotation measure angle. When, so yeah, the way is changing. So the idea here is that the lighter colors is a higher fraction in polarization, and they should follow where you expect the magnetic field to appear in these jets. And then the rotation measure changes to give you an idea that this is an helical magnetic field, right? So you can do these things. Already this is VLA observations, but the VLA cannot actually prove the central parts of these jets, right? The smaller or the weakest components, right? So this one, the ngVLA again, that is that you can do more. Yeah. It shouldn't be here. Oh no, it should be here. Okay. What about other stars? Siska and I and other people work in HV stars or similar objects. So what we are trying to do at the moment is the distances to HV stars are not really well determined because the parallax suffer from precise measurements because they are all messy and blobby and they are pulsating. So you cannot really get the parallax very properly. But some other way to do it is to look for masers. For example, SIO at 43 gigahertz, they are very compact in nature. So if you observe it with 6 months in separation, then you can get a proper parallax measurement and a distance that otherwise not even Gaia can do, for example. And the idea of this is to sample basically dusty HV stars in the solar neighborhood up to 1 or 2 kiloparsecs, and then get the maser positions for this with the current VLA. So we are going to do this next year. And then once you have those positions, then you can target them with longer baselines to get the parallax and the parallax for this, and then the distances. So this is just a plot showing you the dust production rate in these HV stars, color coded by tiers. So these are more dusty, the ones losing more mass, and this is the distance. These are actually actual measurements for the VLA at different frequencies for masers. So the idea is that we are targeting this color-coded sample. And then because these ones have detections, then we expect a good detection rate for these, yeah? And then you will say, well, okay, yeah, you already can do it. The problem is that with the VLA, you can get the line for the maser line detections very quickly. But if you want to do an experiment for astrometry, it takes you several hours per source. And if you have hundreds of them or hundreds of AGB stars in the solar neighborhood, nobody's going to give you the observing time. So if the ngVLA can do 10 times better in sensitivity, then you can do this in a systematic way, right? Maybe not all of them, but you can, it's already a start, right? Yeah. And another thing what you can do for AGB stars is that this is basically, those ones are SIO masers, but you also can do things in continuum. So you have the shell around the AGB star, but because the BLA is the ngVLA will be very sensitive and high angular resolution, you can actually start to see the photospheres, well, the radio photosphere, right? Not in the optical. And then you can actually see changes in time, right? So the ngVLA, the idea of the observatory is that you also can do astronomy in time, right? Not just one single image, but changes in time, essentially. All right. So in this second part of the talk, I will go a little bit in a summary for the collaboration with UNAM in Mexico. So back in October last year, NRAO signed basically a memorandum of agreement or a collaboration with the National University in Mexico, and well, with the team. And what are we going to do in this collaboration? Okay, so already we participate in this. So we have the Science Advisory Council, the Technical Advisory Council. So we have some people that is more working on the science, some other people that know more about the observatory stuff, like Stan or myself. And then the idea is to also develop science cases, and we need to work in the array configuration, define antenna locations, do synthetic simulations, and some other things. Yeah, and a current breakdown is like this. So I'm color coding the ones that belong to the same category. So the characterization of the mid-array sites in Mexico, some simulations, and we also, of course, need to, for characterizing, you need to monitor those places. It's not just put an antenna there. You need to make sure the site will be useful for radio. And then we also have some other designs of the components of the observatory, like the antenna foundations or stuff like that. Yeah. Okay, so a little bit of the mid-array sites in Mexico. This is the current mid configuration. So all these antennas here, the Mexico-US border runs somewhere along here. And then basically this spiral is all the way there in a small one. So these red antennas here are the same ones here in blue. So you can see the baselines here, the antenna separation is on the order of hundreds of kilometers per second. These other stations are these other purple ones for the astrometry exercises. So the mid-array essentially is this one, and we have up to 7 antennas in northern Mexico, which are marked here. And how those places look like? Well, it looks like a farming, or it looks like kind of like a desert, very dry and dusty. But you also have things in the mountain, even a little bit wet, like more like a sierra, basically, in northern Mexico. So you have a little bit of everything in that region of the country. And this is very isolated, for example. So what does it mean in terms of observatory? Okay, well, it means that we have to go into the exercise of having digital layers from the government or some other institutions. For example, these ones are elevation contours. This is like 1,500 meters above sea level. Then this is the border with the US. This is the Bravo River. The US is somewhere here on the right. And then these basically areas are towns. These ones are power lines, for example, the main rivers. You have these kind of like more like streams or something like that. These are geological faults here in the mountains. And because this is like a farming area, you have irrigation pipes and stuff like that. The thick black line is paved roads. These ones are dirt roads over here. So you can see some mixture of an environment. So all this one we have to consider. This circle is 20 kilometers in diameter. The antenna is sitting here. Well, at least the ideal position, right? If you follow the design of the observatory, the antenna falls there, right? And but do you need to put it there? Well, not exactly. So if you wanted to do that, then this is another antenna in the mountains. So these are just hills, 2,000 meters high. but there is nothing there, only some streams, only a dirt road here, some faults, but there is nothing, right? This is in the mountains. So it's very difficult to build something there, let alone expensive, right? So what we want to do is essentially take these antenna positions and try to find better locations for them. In particular, these ones that are very remote, or this one that is very close to the coast, because the sea basically push wind with a higher soil content and it's going to corrode the gears of the antenna, stuff like that. So you want to have a high elevation because it's dry, it's good for radio, but then you also want to have your antenna shielded from towns or from transmission antennas that are basically polluting your radio spectrum, right? So if you have like a little hill in between the antenna and these places, then that is ideal. And then you also can move the antenna for a few kilometers or dozens of kilometers, and you don't change the performance of the array. For example, you can take this one, maybe you can move it somewhere here or somewhere here, and this one you can move to the right, maybe. Of course, if you put the antenna over here, then you change a lot the performance, but if you move it within a few percent of the distance to the core, then you are good, right? So that is the exercise we are doing at the moment. And let's skip this one. But there is also more challenges. It's not just finding a good location. You also need to look at the jurisdiction side. For example, all these green areas are parcels, are farming areas, active. And these yellow boxes here, or regions, are what we call, they are socially owned lands in Mexico that you cannot just go and buy a piece, right? You can buy pieces here, but you cannot buy pieces here, or at least not easily. If you want to do something here, you need to formally change the use of soil definition. So ideally you want to put this antenna maybe somewhere here, right? Yeah, to get away from problems. So we have these tables to characterize the type of terrain, the amount of rain, the wind, if the region is for irrigation, or is just dry, or it belongs to the government, or it belongs to private property, right? So this is the summary. We want to shield from contamination in radio. You want to stay within a few kilometers of paved roads because you need the access. And of course, you need to have electricity, a town, because the staff need to go to the town and eat and sleep there. But also you need like a broadband internet access, right? So there are many criteria to decide if a site is feasible or not. Yeah. So as you can tell, nothing of this is related to astronomy when you are building that. We need to come up with the best positions for the antenna, but we also need a lot of collaboration from other people that know about the geology, the soil profile, and there are other critical things more related to law or governments about the piece of land, the transferring of those lands. And then, yeah, so as you can see, this is a multi-discipline project, right? So basically a lot of people or teams need to work before we astronomers can do anything, right? Yeah. So what is these antennas? Why is it so important to put them in Mexico, right? So this is the antenna positions from the mid configuration. This is in meters. So this is like 200 kilometers, like this size, right? Just to give you an idea. You have like up to maybe 1,000. And the center of the VLA here is in New Mexico. And so this is how the antennas that fall in Mexico. So at some point, if you cannot build these antennas, you can say, well, just remove them from the array, right? So what's the problem, right? Or put them somewhere else. The problem is that if you do that, then you get in trouble because this is the PSF, what the radio astronomers call the beam or the synthesized beam, but it's essentially a PSF, like from optical astronomy. And this is just the difference between this and that one is just how you give importance or you weight your data. But in general, as in optical astronomy, you want your PSF as round as possible, right? But you don't want these kind of artifacts outside, right? So you want that Gaussian response in terms of radius or also in intensity, right? And that gives you better images in the end, right? So this is, for example, if you observe a 30-degree declination. So this, in latitude, this is like 30 something. So a 30-degree in declination basically is on top of the antenna distribution, right? So of course the PSF is going to be more round. But then if you go, if you remove those antennas from Mexico, this is the same. But if you remove the antennas, you can start to see that you see some artifacts. Maybe you can say it's not much or it's a lot, but we need to quantify. But if you go to the southern sky, if you want to go to minus 30 or 40 in declination, then your PSF, of course, starts to get very, very long because the antennas are here and you are absorbing basically in a high angle, right? From the northern part of the, not really far from the zenith, right? In that sense. And this is if you remove the antennas from Mexico. So it looks worse, but how much worse? So let's quantify that. So this is just an example of these images. So essentially you can do aperture photometry from this one, like you do in other wavelengths, from the center all the way out. So you average this in azimuth, and essentially if you have a perfect Gaussian response, the dashed line should basically overlap the solid line, and that's fine. It doesn't look too bad, but you can see that the Gaussian doesn't really represent the aperture photometry from this. The residuals are this. So essentially you are overcompensating in some places and undercompensating in this because these two curves deviate. And then you can see in the northern sky is not too much of a problem, but you go to the south in declination, and then you can see the aperture photometry follow this, while it should follow something like this, right? If it was a perfect Gaussian. So the idea is that a PSF is not anymore a Gaussian, and that's problematic because many software tools assume it's a Gaussian, so you need to do different modeling. And then if you want to summarize this, basically you need to look at the ellipticity of that Gaussian, right? In reality, you want to make it like one. Sorry, you need to make it like basically a circle, but you always can have an ellipse, right? So this is just a comparison, for example, of the ratio of the ellipticity of this PSF before and after you remove the antennas from Mexico. So essentially, if this one is 1.8 or 1.5, it means it's 50% more elliptical if you remove the antennas of Mexico, right? And nobody wants to have a more elliptical PSF than you already have. So the bottom line is that you need to have antennas in northern Mexico because you extend the baselines to the south and you allow better PSF when you go to the southern skies, right? Yeah. Okay. So as just quickly to mention that some of the work that UNAM is involved is to build basically the antenna foundations. So that basically the antennas need to sit in a concrete slab that is buried on the ground, but it's not any type of concrete. It needs to have these, basically it's electrically conductive concrete. So basically it's protected for the environment and needs to be very rigid because these antennas are supposed to be super stable when they are slowing, and they are several tons in weight. So you need to have something very heavy, but move it super precisely. And the foundation shouldn't move at all, right? So there is some specialized companies like M3 that design this kind of stuff. Like for example, for ALMA, they know the work that ALMA has to do. So basically this is funded by UNAM and they need to do this design. So how it looks like. So this is basically the concrete slab where the antenna is going to sit. And you have these pillars all this is on the ground. And then you attach the antenna with these ring of bolts somewhere here. And this is like the profile. This is like a notional, right? The idea is that it has to be like this, but you need to design it, engineering, and test it and build it, of course. So this is a collaboration between UNAM and NRAO. UNAM also needs to design the labs. You don't need like a lab for every antenna, but you need one that is close to several antennas. So we also need to design this kind of thing with the Department of Obras Públicas or the public building or something like that. Yeah. So one of these antennas in the northern Mexico should look like this. you have an antenna, you have some lab, or you have a hangar, and you have some power or some other things, and you have monitoring devices for humidity, for wind, for water vapor content, etc. And as part of this agreement with NRAO, UNAM is also acquiring equipment that basically is meteorological stations that need to be mounted in a cart, so you can put it in a station and then deploy it to another station. Not just these values here that can be done with solid state sensors, but you also need to mount for the water vapor column that you see in the direction of the sky, right? The more dry, the better for astronomy in radio. So some of the devices look like this. This is a meteorological station. This is for RFI because you want to see if the sky in that area is really contaminated by radio signals from an antenna or cell phone tower or the town nearby. And this is for, I think this is for temperature and humidity. And this one I think is for lightning in the neighborhood. Because eventually you want to do like this. You want to have the day of the year, and then you want to have the optical depth in that part of the sky, and also the opacity to see how transparent is essentially the atmosphere. And you want to characterize this so you can compare two sides and say, I take this one, right? Because it's better. Yeah. So there are many areas where it's possible to collaborate with UNAM in Mexico, but also with NRAO in this project. So there is a lot of infrastructure needed. And then as I told you before, there is these other areas that we need to tackle. So we need to collaborate with other departments or the universities in general. So there is also the other component of how we approach this from the community point of view. So last September, just like 2 months ago, we have the first Mexican workshop for the ngVLA. So essentially, all these people and some of the contributed talks were about the science that you can do with the VLA or the current status of the observatory. This is basically was a Mexican meeting, and these are the people that are working on the project, or at least the people leading different parts of the team. And then one thing that is coming very soon in terms of planning and something like that is that we are going to host an international ngVLA conference in Mexico next year, like a year from now, sometime in between October and November. And this is going to be hosted together by NRAO and UNAM essentially. So it's going to be an official, more official ngVLA workshop. So everybody is invited. The first announcement should be going out in this month or maybe early next month. And so this is going to be hosted most likely in Morelia. It's a beautiful town. You've never been there. So yeah, if you are interested, you can try to join this. Yeah. Okay, just a quick summary. So this is an international collaboration. Some of the good news is that the project has budget to do the conceptual review, the preliminary review. They are also already building the prototype antenna, so it's already ongoing. And but of course, it's not set in stone that it's going to be built. But from the NSF point of view, or the collaboration between NSF and NRAO, it looks like they still like the project, so it can happen. Yeah, and that's all from my side. Thank you.
Thanks, Alfonso. I have a question.
I have a question when you were there, the survey observations, because I think you have 200 antennas, sometimes 40 antennas. How are they going to be? They're going to be done in the same way as the VLA is doing now, or you want to take the SKA?
Essentially, in terms of processing, the observatory will do it. We don't expect the people need to do it in the institute because the computing power and the space is way demanding. So the idea is that the observatory should do this. And if you want to reprocess, it's possible because the idea is that the project will keep the original data, but it will need basically a supercomputer to process it. Yeah.
There's a lot of
Yeah, because the volume of data, for example, in ALMA, after 1 hour of observing time or something, it can be a couple hundred gigabytes, but this is going to easily be a factor of 10 higher because you have many more antennas, so you cannot really process that in outside. I mean, it's possible. Maybe only institutions, for example. Some people are already trying to trial how to process this using supercomputers in the University of Texas, that they have this kind of infrastructure already. So there is already a partnership to try to explore how to process that. Yeah.
They also want to an archive like ALMA.
Yes. Yeah. The idea is that you should keep everything in archive. Just it will be much larger. Yeah.
Any other questions? Well, I have a question. Can you, I mean, kind of related to this, can you expand a little bit on the plans for the speed instruments? Because from ALMA, we know that it's a huge effort to maintain, 8 or 10 bands
Right.
on 66 or 72
Right.
antennas.
Yeah.
But now you're going to have 240,
Yeah.
So are you thinking about simplifying the instrumentation suite compared to ALMA, or
Yes, I think yes, in a way. So the number of bands here are 6 to cover all these 1 to essentially 120 gigahertz. And then in this figure I was showing here just about like a basic layout of a site, is that these kind of hangars or labs should have spares in terms of receivers, so you can just replace one in the antenna if it's broken. And there is going to be other like main hubs for where the engineering team need to work on receivers and stuff like that, maybe more like in NRAO. And the other thing is that in principle, the antennas are designed to need as little maintenance as possible, because as you say, you cannot do this 200 times. So the idea is that the surface or the maintenance of the gears or even the cabin where the receivers are hosted, then it should be much more stable than ALMA, for example, because otherwise it becomes super expensive to maintain them. For example, they were even doing some analysis of you need to recoat the dish with some paint or whatever, then even that exercise becomes super expensive because it's 240. Then even at that level needs to be designed to endure.
Right.
And the other thing is that compared to ALMA, these ones are not located in a harsh environment like the Atacama Desert, where there is snow and freezing. So these ones are essentially 1,000 meters over the sea level. So they should not see any freezing or stuff like that because they are not designed for that. So we also need to account for that to find the best sites.
But if you have in each of these sites, you have a spare for every band, then you need to have.
Sure.
You need to have a lot of copies of every band. No?
I don't think they are planning to have a spare for all of them.
I guess in the central compact part, you don't need so many spares, no? But in the remote sites, you're going to need.
So the idea is that maybe there is this building here, but there is another station, say 50 kilometers away or 100, and maybe there is nothing like this of this building. So these centers are more like serving regional areas. But I agree that you cannot have too many spares.
I mean the instrumentation, if you have 6 bands times 240 times some spares.
Yes.
Some spares. I mean, this is going to be huge in terms of
way too many.
Okay. Are there any other questions?
Yes, thanks a lot. That was very, very interesting. And more on the legal side that you mentioned. About that, you write about it, but sometimes the less may be there is some farming going on. So do you know how these things are going to work to negotiate? Well, first of all, if these farming lands are big companies like Monsanto or are local farmers, and second, if it's the latter, how is this going to work in the negotiation? Is something similar to when you build a highway, then you kind of pay a little bit and you evict them, or how?
Yes. So yeah, that is a very good question, and then we haven't sorted out. But the way things are, the US is different from Mexico. That's another thing in terms of land ownership. Mexico essentially has basically land belonging to the federal government, private property, and we also have land that belongs to the municipalities or the state governments. And then we also have this system that we call ejidos and comunidades that is essentially socially owned. So there is, for example, this small town here or this one together, or not all the town, but maybe a group of people in that town owns maybe this part here, right? Or this block of land here. And legally, they only can use certain fraction for housing, certain fraction for farming, and certain fraction for communal activities. And you as a private entity cannot go and buy a piece of this because it belongs to a group of people. But it's possible under the law to actually make it happen. It's just that it's more legal work to do. The other thing is that I don't have a slide here, but we also have national parks. And then the LMT, for example, or other observatories sit inside national parks. And that basically makes you to do more environmental studies and also cultural studies, because you also need to make sure you are not like invading something that can be very sensitive for the local population. And yeah, so it's more effort to do it. Of course, if at the end there is no choice, we are going to put it in a national park or in a ejido comunidad, but we need to make sure it can be, we need to make sure the land can be used by the observatory in a few decades. Because if you don't have the legal warranty in these socially owned lands, they can tell you, oh, just give me my land. I want it back. Right? And so we want to look into those things. So that's why we want to basically put things outside these social entities or outside national parks. On the other hand, because national parks are protected, then you don't expect much development around. So you can have a more like a free from interference area. So there are also other advantages to be inside a national park. So we need to weigh these two approaches. And we need to definitely work with the departments of the university that know much more about the local area and culture and everything. Yeah. So
but this is done by you, or it's all via local government?
In principle, it needs to be more like the local government. UNAM has a few campuses in the north, but essentially the idea is that we need to form some sort of consortium with the state universities that are interested in the north. And then through them, you can approach the state government. And somewhere in that connection, you need to approach these lands to make it more smooth. And so we can do our work and we don't bother them, we don't affect them. So it has to work in both directions. Yeah. Yeah.
Okay, any other questions?
Not that is one online. I don't know, Chema, if you want to unmute yourself and ask the question.
Is there any question in the Zoom?
Gemma.
Yeah. He could hear me, but I'm not sure.
If not, he's writing here. He's just well, congratulations you UNAM for the agreement reached with NRAO, and he's also asking if it's necessary any agreement between the USA and Mexico, the level of governance to allow to install USA antennas in Mexican territory.
Okay. Not sure I know the answer to that. Right. Yeah, because this is a multinational project, or will be in principle. I don't think there is anything that prevents you to install stuff from other countries in Mexico, as long if it's for academic purposes. In a way, it's easier than if it's for companies or other things, because it's kind of like non-profit organizations. So I know it's easier, but it's a good question. Yeah, I will have to go and ask the university if we need some other agreement, right? Because it might be US properties. That's a good point. Which is also something we need to discuss, because we don't know yet if Mexico needs to put money for some of the antennas or we only host those antennas, right? And maybe we provide some other type of support or instruments or something, right? That's still to be decided.
So when do you plan to have your site selection and site acquisition finished?
Right. So the idea for this is that because the preliminary design review, the way they call it, is a couple of years from now. So at least we need to have this ready. Maybe it's within 1 year, something I would say. I mean, on the computer, with or using all these digital layers, I can come up with some good numbers early next year. But to visit the sites and start to do some monitoring, you are talking about at least 1 year scale, to have an idea which one is better. Yeah. Yep.
No. That's it.
Okay, if there are no more questions for you, can just thank the speaker again.
Thank you.
It should be